Today I will talk about some remarks on the supersymmetry, first of all the dynamical supersymmetry breaking, and the second one is a mu problem and the resolutions of this. First one is NMSSM and the second one is the Kim-Nilles mechanism. So first I will review on the dynamical supersymmetry breaking, DSB burst. DSB provides the manipulated action and scalar potential, so the potential smoothly decreasing to zeros at the partial infinity. Such a dynamical supersymmetric Viking cellulitis with the dynamical chiral symmetric Viking. It can be distinguished with the chiral perturbation theory. If the NO scale is smaller than the cutoff scale of the QCD, then the Lagrangians are described by the effective field theory in terms of the pion decay constants and its mass. But in the dynamical symmetric breaking, there are no external sources. The self-generated breaking occur, and from the non-perturbative effect, the cutoff scales are given by the multiplications of the exponential factors and the Planck scale. So they generate the cutoff scales naturally. And such an example of the dynamical symmetric breaking is technical thing. So in the dynamical supersymmetric breaking, there's some super potentials in terms of the number of the fermions and the number of the color gases. And similarly, there will be some condensate with the two chiral superfield, and from these potentials, it can provide the involved power potentials naturally, which can be the quintessence models potentials. Such a dynamical supersymmetric breakings, the supersymmetric breaking scales are naturally generated with the non-perturbative effect. And there are several possible choices that we already saw the superpotential, which is holomorphic function of the matter field. So there are no conjugates of the chiral superfield, but also we can use the chiral potentials, which contain the kinetic term, complex conjugates of the chiral field. Second, I want to discuss today is the combination of the axion and the supersymmetry. There's a very well-known model, Kim-Nilles mechanism, which can be the resolution of the mu problem. The U1 PQ symmetry with the axion can solve the strong CP problem, and the supersymmetry contains the mu problem. And we can combine the two things, because axion, there will be the axion decay constant, and also for the supersymmetry, there will be the supersymmetry breaking scale. The axion decay constants have the roughly 10 to the 9 CV to the 10 to the 12 CV. And the gravitational mass is given by this such a form, f over the m Planck, about the root of the supersymmetry breaking scale. So if we consider the following superpotential as a DFS model form in the Kim-Nilles mechanism, there will be the coupling between the single left field S scarce and H1, H2. Then here's M Planck is the reduced Planck mass here. And the BAP S provides the axion decay constant scale, which is called the intermediate scales, from 10 to 9 to 10 to the 12 CV. So the axion scales are determined by the supersymmetric breakings, and the superpartner of the axion, which is called axion A tilde, scatter mass by the supersymmetric breaking, and this can be the RSP. The typical scales of the axions are determined by the following form. The axion decay constant has a 10 to the 12 CV is a typical scale, and the axion mass is given by 10 to the minus 6 electron volt. The axion potential is given by the periodic form with the cosine potential, and if there are some of the coefficient lambda 4, which is lambda is the cutoff scale, then axion mass is given by the lambda 4 over the FA scale. So that we can obtain the axion mass in terms of such a form, and because there are some relation between both the strong CP problems and the axiom thing, so the multiplications of the axiom method and the PQ scale is the same with the pi method and the pi decay constant from the to resolve the strong CP problem. In the axiom model, the axioms are coupled with the GG tilde to resolve the strong CP problem. The supersymmetric version of this vertex is given by the A tilde, which is axinal, and the G tilde, which is the gluonal. So the such an axion T-gluon vertex becomes axinal gluon vertex, and still there will be the one of the A factor dimension. If we consider dimensional analysis, this axinal and gluonal is the fermion, so 3/2 and to the 3/2, and the pure strength of the gluons has the mass of the two, so there will be one of the A is a coupling constant. So now let's consider the mu problem in the supersymmetry. The mu is a supersymmetry conserving parameters, and the soft mass is a supersymmetry breaking parameters. So the scale of the soft mass is given by 1 to the 10 TB, but the mu is 100 to the 1000 CB to give the lactal Higgs-metric breaking, and these have the similar order, and to give the standard model Higgs mass. The resolution of the such a mu problem is the before the symmetric breaking, if the mu terms is equal to 0, so level, and if the mu get the BAV, mu is given by the BAV of some singular field depending on the supersymmetric breaking scale, then the mu term can be naturally generated with the similar scales with the supersymmetric breaking scale. So there are also several possible resolutions for the mu problem. One is NMSSM, the next minimal supersymmetric standard model, and the second one is the Kim-Nilles mechanism that we think about this with this superpotentials coupling to the Higgs. So this S scales H1, H2 gives the also mu terms, and also gives the axiom scale. Already we talk about it here. So this generate the effective mu terms naturally, and also the observers gives the axiom scale. This is the mu terms already we talk about. And the third possible choice is due to some isolar mechanism. This is color potential instead of the superpotential. The electroweak metric breaking conditions in the supersymmetry should consider the 2x model because there are 2 Higgs. So the electroweak metric break conditions are given like that, and there are negative soft mass here. And since this is electroweak scale, and this terms is determined by the soft scale, supersymmetric breaking scale. So to give the exact electroweak metric breaking and the scale, mu term scale is also similar to the soft scale, supersymmetric breaking. So here is some expansion in the large beta case. So here is still electroweak scale, soft mass, mu term, and to give the 100 CB electroweak scale. The mu term also helps the similar scale to the soft mass scale, and significant cancellations in the study. The first last solution of such a problem in the NMSSM, we can add the singular field S. So here is the superpotential in the minimal supersymmetric standard model, and we can add the singular field coupling SHUHD. So the lambda S gives the mu term, effective mu term naturally, and there will be the S linear coupling term and the quadratic coupling term. Then also the this is a supersymmetric conserving superpotential term, and for the soft mass there will be the additional term SHUHD, which is I term, trilinear term, and the S and the trilinear, bilinear, and the tadpole term. So this S is a super field here, and this S is just a scalar field here, and also the soft scalar scaled mass term will be added. The effective midterms are generated through with the lambda S, and the scale of the midterms becomes similar to the soft mass scale. But there will be some of the problem because the because of the some linear term, there will be some discrete just 3 symmetry will be appear, and that is might makes the domain more problem in the cosmology. And with the additional soft mass term with the singular pillars and additional superpotential term with the singular pillars, the electroweak symmetry breaking conditions also changes. And the neutralino factors includes additional degree of freedom with the single linear, so the matrix is the extended by matrix. The other possible resolutions of the problem is the mu terms are generated from the non-normalizable terms through the high dimensional sort of light. One can use a superpotential. This is the Kim-Nilles mechanism. Also gives axion decay scale, PK scale, and the other choice is the color potential sort of with the complex conjugates. This is called the Judichast-Majoran mechanism. So already we saw that the Kim-Nilles mechanism. We can assign the PQ charges about the Higgs field and the Caucasian leptons and the light-handed one. Then the superpotential can contain such a form. And the S get the -1 here. Higgs get the 1 here is the PQ charge. So this is -2 for the scale. And the PQ scales are determined by the waves of the singular field S. And the for supersymmetric Viking scale to be down, then this term lambda S scales over the Planck scale should be similar to the soft mass. So this is the effective midterm generated by the waves of the S here. And also for the soft term, the former ones the superpotential with the supersymmetric conserving Lagrangian, and also we can consider the soft term with the following form, and this gives the effective midterm. The Judichast-Majoran mechanisms use the color potential, so that there will be the conjugate terms here with this term, and if the X get the BAP with this octalar field, then the effective midterms also can be generated. So here is an overview. Singular field S gives the PK scale. This gives axial mass, and also the effective midterms are generated from the singular fields of the S.